pH and pOH. Hydronium ion concentrations in aqueous solutions can vary between 1.0 molar and 1.0 times 10 to the minus 14th molar, where the first part is very acidic and this is very basic. Because these values are very small and have negative exponents, it's more convenient to express them on a log scale. This is where some cool math comes in. pH will be defined as a negative log base 10, okay, so we're not dealing with the ln, of the hydronium concentration when concentration is measured in moles per liter. A lot of words there, but if you use the math, look how quickly you can write it, okay? These two things are equivalent. So if you have a neutral aqueous solution at 25 degrees Celsius, we write pH as, it's a negative log base 10 of 1.0 times 10 to the minus 7th molar, and molar comes out because that's a unit, and then you have negative of negative 7, pH of 7. That's actually neutral, right? pH 7, same thing as saying neutral. Let's go to both extremes of hydronium ion concentrations to see what we get. We're going to calculate the pH for highly acidic, 1.0 molar, and highly basic. So go ahead, use the equation from the previous page, plug that into your calculator, and what do you have? There's your neutral solution from the last slide. Mostly acidic, you get 0.00, and highly basic, you get 14.00. So the pH scale ranges between 0 and 14. In practice, the range can be lower than 0 or greater than 14, but the ionic constant of water still holds. This scale shows the advantage of using the pH scale. Over here are your hydronium ion concentrations. If you want to say it's 1.0 times 10 to the minus 14th molar, you have to write all that out. But if you use the pH scale, that's 14. Likewise, down here for something very basic, you can either write this or this number. And correspondingly, you can see the power of the exponent turns into the pH number. So very basic up at the top, very acidic down here. Now you just have to get familiar with what's going on. For your example, you go from here, 10 to 12 doesn't seem like a big number, right? It's only 2. However, since we're using a log scale, the difference between each measurement represents a 10-fold change. So a difference of 1 pH unit is a 10-fold change in hydronium ion concentration. It's multiplied by 10. A difference of 2 pH units like you have here, that means you have a 100-fold change in hydronium. If you're 3 pH units different, that's a 1,000-fold change in hydronium ion concentration. So what's happening here, I'll draw it here, 10, 3, right? If you have pH differences 3, your concentration is 10 to the third or 1,000 times different. What's the relationship between the hydronium ion concentration and the pH value? Here we have 3 different hydronium ion concentrations. Find the pH of each. And here's our equation. So go ahead and give that a shot on your own, and then we'll fill the answers in when you're done. Okay, let's look at this first one. Log base 10 of 10 to the minus 1 is minus 1. You then have to multiply it by this negative. So you get a 1 here. Here, log of 10 to the minus 2 is negative 2. Multiply that by a negative 1. You get 2. And then down here you have 10. So what can we say? The lower the hydronium concentration, and where are we the lowest? Right here. What do we notice about the pH? It's the highest. So we'll draw an arrow up, or you could just write the highest the pH, or the higher the pH. A logarithm has the same number of places after the decimal as there are digits in the original number. So here's our original number. This is our concentration of hydronium ions, and we want to find the pH. So we have our pH formula. We put in our concentration right here. And you can see there are 2 digits, 1 and 2. We take the log base 10 of that, and we're going to write negative 4.92. multiply it by -1, and here's our pH. So there's our 2 decimal places, because we had 2 digits in the original number multiplied by the 10 to the minus 5. So here's our order. Take the log of the number first, then reverse the sign when you multiply it by -1. And I know I say don't do this, but go ahead and give that a try and see what your calculator comes up with. Yeah, it's not defined because you can't raise 10 to any power and get a negative number. So this is not good. You reverse the sign when you're all done taking the log. Then you check. The hydronium ion concentration is lower than 1 times 10 to the minus 7. Therefore, the pH should be acidic and less than a pH of 7. And of course it is. It's 4.92. For proteins to be digested in the stomach, the pH must be lower than 2.7. If the pH is too high, proteins will not be broken down and may cause indigestion. So let's pretend you're a doctor. A patient comes in complaining of indigestion. A sample of stomach fluid is taken, which is pretty disgusting, and the hydronium ion concentration is found to be 3.4 times 10 to the minus 4 molar. Is there a reason for the indigestion? So please attack this problem before we pull out the answer tab, and you should probably go ahead and find the pH of the solution using the formula. So take a couple seconds. Okay, now we'll see what the answer is. When you calculate the pH, which is a negative of the base 10 log of the concentration, you get 3.47. So that's not as acidic as you'd like for the stomach. So it's likely that proteins are not being degraded, and that may be the cause of the indigestion. Let's calculate the pH of a strong acid. And by the way, calculating the pH of a weak acid is much more complex, and we're not going to do that. Previously, we talked about strong acids completely dissociate in water. So it goes over to 100% of the chloride ion and the hydronium ion. Calculating the pH of a strong acid is easy as long as you know the molarity of the answer. So if we're asking what is the pH of a 0.25 molar solution of hydrogen chloride, or hydrochloric acid, well, if we know it's 0.25 molar, then the molarity of the hydronium has to be the same. Why? Because the coefficient in front of the hydronium and the HCl is the same, it's 1. So we use our pH formula, minus log base 10 of 0.25, and we come up with a pH of 0.60, which is very, very low. What if you'd like to go the other way? You would like to find the hydronium concentration, and you're given the pH. So we're going to do the opposite operation. The first thing you do is multiply the pH value by -1, and then this value is raised to the power of 10. On a calculator, input the value for the negative of the pH value, so you'd write in -7.89, for example, and then select the 10 to the x key. Sadly, that doesn't work for every calculator, so I just used the one I had, and turns out you punch the 10 to the x key first, then you put in the -7.89, and then you put enter. So you're going to have to fiddle with your calculator to see which way you do it. So let's get back to the math. But the point is, you want to get an answer that is this right over here, okay? So here's the equation. 10 to the minus pH is equal to the concentration of the hydronium. So in this case, we give you the pH is 7.89. You plug it in over here, and then you figure out how your calculator gives you reading. And you want to get an answer of 1.3 times 10 to the minus 8th molar. Note, there are 2 decimal places in the pH value, right, 8 and 9, and therefore 2 significant figures in the hydronium ion concentration. Please try this problem on your own. What is the hydronium ion concentration in a solution of lemon juice that has a pH of 3.51? So you have 2 decimal places there. So go ahead and work that. When you're ready, we can pull out the answer tab. So pause it if you need to, and if not, here we go. And what we do is 10 to the negative 3.51, and see how there's 2 decimal places there? So my answer will have 2 figures here, 3.1, and this is my concentration, which you write this way, H3O plus, and you put the bracket on the other side. What if you wanted to represent these concentrations on the pOH scale? Well, here's how we did pH. So can you figure out how we would do pOH? Same thing, except instead of the concentration of hydronium ions, you use the hydroxide ions. Now these concentrations are inversely related, as we talked about earlier. Therefore, pH and pOH are also inversely related. So when you have a low pH, such as 0, you'll have a high pOH, like 14. They both meet in the middle at 7, and then you have a high pH of 14 and a low pOH of 0. Let's calculate the pOH of a solution that has the following concentration right here. Use the equation. pOH is minus log base 10 of the concentration of the hydroxide ion. And again, make sure this is a positive number. You can't take the log of a negative number. Carry out the math. We have two figures here, so you want 2 decimal places. So your answer is 4.64. If you have a solution with a known pH, it's very easy to calculate pOH. And let's go through the math. It's kind of fun. Now remember, this is the ionic constant of water. This stays the same. And the ionic constant of water is given by this expression right here. So if I were to take the negative logarithm of that, we get P of the ionic constant of water. P means the negative logarithm. And then you take the negative logarithm of each of these guys. Well, let's see if we remember this. The log of A times B, you should have had this in your math course at some point, is the log of A plus the log of B. So this multiplication here turns into an addition, and this pH, that's the log base 10 of the hydronium oxide concentration, and this is the log base 10 of the hydroxide ion concentration. So they just come down here. Now my only thing I have to do now is find the pH of this. So that's minus the log base 10 of 1 times 10 to the minus 14. And that's just 14. You can check with your calculator. So our final answer is 14 will equal your pH value plus your pOH value. Let's try an example. We have lemon juice with a pH of 3.52. What is its pOH? Here's how we relate them. We write it down again here, and we kind of skipped a step here. We actually said pOH is equal to 14 minus pH, and then you plug in the pH of 3.502, and pOH is 10.48. What if we're given a pOH value and we want to find the OH concentration? We do it the same way we did with the pH, where if we had pH, we could find the hydronium ion concentration by this equation. So if we have pOH, we can determine the hydroxide ion concentration. So let's have a pOH of 12. Here's our equation right here, right? Comes right down from there. Put in negative 12 for the pOH, and then put that on your calculator, or just realize that 10 to the minus 12th is 1 times 10 to the minus 12th molar. We can make these a little more tricky. For example, if we want the concentration of the hydronium ion, when you have a pOH of 11.4, there's an extra step you have to take. You start with this equation here, find the pH when you're given the pOH, and you get the pOH is 2.6. Then you just go 10 to the minus 2.6 is 2.51 times 10 to the minus 3 molar, and that is the concentration of the hydronium ion. And this one here serves as a model for some of the assessment questions that follow.